Good afternoon. I hope everybody's having a good day today, and I appreciate all of you being here. Today, I'm going to start with something that I don't think will be controversial by the time I'm done talking, but you can talk to me about it afterwards. I'm going to start out with telling you that AI has broken hardware, and we're going to talk about where do we go from here. So, to say a little bit more about that, I'll talk about where we're going to end in our future state. So today we heard from a number of speakers this morning talking about how AI is the future and how all these new workloads are going to enable amazing things. And I actually agree with that. I believe that AI will bring unprecedented productivity gains that will change the roles, the jobs, the products, and the way we live our lives, as we heard from all the speakers this morning. And in fact, I think it will be as impactful as the internet. So there's no problems, correct? Well, actually, there's a bunch of challenges right now that are facing us as we think about building these massive systems that it takes to bring all these new AI capabilities to you. And so what I'm going to do in our time together today is talk about what's happening in the hardware space and kind of across all these platforms that we're building to address some of these core challenges. I'll start out with a little bit of silicon. Many of you have probably heard how Moore's law is slowing or ending, which means transistors aren't getting smaller and denser. In fact, the costs are going up. That Dennard scaling, which also relates to getting more transistors on a given die at a certain price point, ended in the middle of the early 2000s. So those are huge engineering challenges. Meanwhile, AI, which has been talked about and dreamed about since the 1950s, is finally here. We finally have enough compute, right? The amount of compute available to scientists and engineers has been growing since the 1950s, since the modern computer was created. But what's happened as you look at this chart is there's a big bend in it. And what this chart shows is the number of flops, or the number of computations needed to train some of these very large models. And you can see in the last few years that it's taken a huge, huge change. And in fact, it's gone to a 10x increase year on year. And so, meanwhile, as the technology is slowing, the need for more performance is growing at a 10x rate. And this is creating a huge challenge for us in the computer industry. And not only is the need for more performance for these larger AI models higher than it's ever been in the history of compute, it's happening at a time over a shorter time window. So today you've heard a lot about ChatGPT and GPT-4. Well, the underlying technology is something called transformers that we also heard about this morning. But the original paper was written at the end of 2017, and the first transformer model was developed in 2018. So in a handful of years, we've gone from the first transformer model to something that has the capabilities of ChatGPT and GPT-4. That's part of this massive 10x increase in the need for compute performance. But if you look at traditional semiconductors, whether this be a large CPU or a large AI chip from the likes of Intel or NVIDIA or AMD, their typical development cycle is 4 years. So we have a further problem in that as the technology of semiconductors has been slowing and it's harder to extract more performance, we have this long development cycle and AI has been accelerating. And in fact, we've gone from the first idea of the first transformer to GPT-4 in 5 years, and that's not even 2 hardware cycles. So when I say that software and AI has broken hardware, this is one point on that curve, that the hardware just is not being developed quickly enough to meet the needs for all these new models. And that creates additional sets of challenges. And very specifically, when I talk about how AI has broken hardware and the limitations that we're facing, as we've had this problem with semiconductor scaling, we then are trying to build larger systems to make and accommodate these super huge AI models that are commonplace today. And so there's kind of 5 areas where these larger systems and the growth of AI has fundamentally broken hardware. The first is just the need for more compute. If I can't extract more performance from a given chip, I need more of them, and then I need to string them together into really large systems. Well, the interconnect for that scalability has been stretched to its limit. You just cannot connect these chips together at a high enough rate to continue to raise the performance. The second area is around memory limitations. The first AI models were super compute intensive and didn't need a lot of memory bandwidth. When you look at transformers and recommendation engines and other larger models that we're experiencing today, they have a huge memory bandwidth issue. And they also don't share memory, so you need even more memory to go in every system, which generates heat and cost and challenges of scalability. The next piece is the hardware-software co-design hasn't really happened as much in the AI space as we've done in the computer space over the years. So today you have a lot of hand-tuned code that is optimized for unique hardware. And compiler development is behind what you would get for a normal CPU. In fact, a lot of the initial AI components will have these small blocks of code that have been hand-optimized by an engineer. So it's very hard to scale those because you can only scale them as quickly as you have engineers to optimize that code. And the design targets, as I mentioned, were completely wrong. They were thinking that compute was the bottleneck because it was for small models. But as you look at these large language models or foundational models or things like ChatGPT, memory is really one of the major issues, and memory bandwidth. The next piece is cost. Since we're building these huge systems to train and use these huge models, it's incredibly expensive. It is tens of millions of dollars to train some of these large models. And that means they're essentially not practical to deploy at large scale. And so while everyone is talking about ChatGPT, it's actually a relatively small, restricted workload versus what we'd really like to do with AI. And the current technology just does not allow that. The last piece is reliability. As you build these larger systems, it gets harder and harder to scale them and to make the hardware and the software work as a reliable way. And in fact, a researcher recently wrote a paper talking about how 15% of their supercomputer cycles are being used in a technology called checkpointing. Essentially, what that means is they're using 15% of the potential compute bandwidth to just keep track of where the model is as it goes, because the machine fails so often that they actually have to, as it fails, reboot it, go back and restart it, and the checkpointing allows them to do that. So they're using a huge amount of overhead just to try to keep training these models because it's so hard to scale these systems. And then on top of that, there's been a number of papers that have been written around data corruption. And the idea here is as systems get so big, they get hot, they get noisy, electrically noisy, and well, also physically noisy with all the fans, but electrically noisy, such that you're getting data corruption errors. And this changes how models work, and it becomes very, very hard, again, to train these larger models. So AI has kind of broken the hardware space. Maybe we'll go to the next slide. Thank you. Okay. The other challenge, so I talked about all the hardware challenges that we're having with software to build these large models, but on top of that, countries around the world, in fact, over 100 countries by most recent count, are having a whole bunch of set of rules around what we call data sovereignty and residency. And this is the idea that data created in a country like Korea cannot be stored on servers outside of Korea. And there's 100 countries that are passing these kinds of laws on a global basis. So as if it wasn't hard enough to build and train these huge models, now the data that you're using to train them, or the customer data and the personal information that you're storing, has to be stored in specific countries. So this is regulations adding more complication to these massive amounts of data that we're trying to process. And then one of the other parts is just the huge amount of data that's being created, right? This is a chart showing the number of enterprise zettabytes of data that are being deployed. And this is probably about half of the overall data storage. It's a little hard to get cloud storage numbers. So these are the enterprise data. So think of this as data going to large companies. And just to try to put some context on a zettabyte, which I'm not sure if everybody knows how many zeros that is, but this device is a small single chip SSD, a solid state drive with memory devices in it, right? And this device holds 1 terabyte of data, which sounds like a lot, right? It's hundreds of thousands of photos that can be stored on this teeny tiny little device. But if you had a zettabyte of storage, you would need 1 billion of these. So the industry is creating data at a massive rate. So this is storage that is getting deployed to store all these zettabytes of data. So on top of the hardware challenges and the software challenges, we have regulatory challenges about where data is stored. Meanwhile, we're generating huge amounts of data that make it even harder to run these huge systems. And then, of course, the last part is power. I think many people have read how these large data centers are consuming more and more of the global power, right? It's great that, as Vinesh just talked about, we're going to have more capability on devices like our phones, but currently these large models are consuming huge amounts of power in these large data centers. In fact, the data center that is in Council Bluffs, Iowa, if some of you know where that is, that's in the United States, in the middle of the country, has a very large power plant near a river, and it's one of the data centers that Microsoft uses to help OpenAI train their large models. And recently, there's been a whole bunch of frustration and anger because that data center, for cooling purposes, is consuming up to 10% of the fresh water in Council Bluffs, Iowa. So they're now worried that they won't have enough water for the people that live in the town. So these are very, again, real problems that as an industry we're going to have to face if we want to keep doing this. So this is another thing that complicates what we're doing and why I say AI has broken hardware. So I shared a lot of the challenges that we have as an industry. So you could ask, is this kind of the end of semiconductor improvements, right? Have we reached the end? Will they never get any better? Will compute performance plateau? If we can't put more chips together and we can't build more powerful chips, are these the biggest systems that we're ever going to have? And we've reached the limit, right? Was just reading an interview with a scientist, and she was saying how while ChatGPT and GPT-4 are amazing, they have roughly the mental capacity of a squirrel, right? The small little rodent or mammal that grows in the trees. Clearly, we would want to build bigger models that had more capability over time. So have we reached the limit of what we really can do? So what do we do? Where do we go from here? I've been involved in semiconductors basically my whole career for over 30 years. And one of the things that I think is really important that maybe a lot of people don't realize, especially if you haven't been in semiconductors, is that Moore's law was not a given. It served as an inspiration for the engineers that were developing the technology. I worked at Intel for 30 years. If you talk to the engineers that were building the process technology and the devices that went into that created those chips, they would tell you that Moore's law served as an inspiration to spur them on to create new capabilities and new technologies. So again, it's really innovation across all of these platforms that created the opportunity that it's gotten us this far. So I fundamentally don't believe that all these limits that I talked about and all the challenges that we have around expanding AI and how it has broken hardware is not something that we can't work through. In fact, the things that I'm going to talk about for the rest of our time together today is really talking about how there's an innovation across our industry that's going to enable at least 100x improvement in the capabilities that we all have access to. And that's what's really going to enable some of these future capabilities that we talked about this morning, and I'm sure that all of you have in your mind when you think about AI. As a little bit of context, I wanted to use this super simple model to talk about some advancements and changes that are happening in the hardware space. And the idea here is that if you think about a computer, it's really kind of three things. One is you have the compute thing where you have data and you're doing work on it. This is a traditional workload if it's a database or a spreadsheet or an AI model. You need compute hardware that can process that data and give you responses. The next piece is memory and storage. When data isn't being processed, you need to put it somewhere to store it and manage it. And that's what memory and storage is for. The third piece of the triangle is data movement. And data movement is all about moving it from one location to another, right? This is how you display graphics on a screen, or how we do digital phone calls, or how you get responses from ChatGPT. The last piece that I'll talk about here is the packaging piece, because while all these technologies are interesting, packaging is going to play a critical role, as you'll hear in the rest of my talk, about how it brings all these different capabilities together. So starting with compute, because I think it's one of the most exciting parts, is One fundamental move, and maybe you've heard this, is the move from chiplets, or from monolithic die, large die, into chiplets and 3D packaging. And again, this is one of the things that the industry is doing to try to get around some of these Moore's law limitations, right? If I make smaller chips, I can get higher yield, I can lower the power, and then I can put them together on a substrate and actually build a larger system and have it communicate. And that's starting to happen now, right? There's a lot of recent announcements in the industry around taking smaller chiplets, putting them on a substrate, and creating a powerful subsystem. But sometimes that's not enough, right? Another thing that is very popular and is growing and is a fundamental part of how computing will advance is something called domain-specific architecture. I know that sounds complicated and fancy, but it's simply the idea of the generic CPU that does all kinds of workloads has been around since the 1970s. But going forward, since Moore's law scaling is not giving us more transistors in a given area, what we do instead is build something that has a unique set of capabilities. It's a smaller die, or a die that only does AI processing, right? It can't process graphics. It can't do generic things. It's a unique product designed to do a specific set of workloads. And what you'll see is there's a large growth in this space. AI engines and a lot of companies are doing domain-specific architectures to try to address the needs of scaling to larger models. And when you take a domain-specific architecture and you couple it with the chiplet, now you'll be able to see companies build very large subsystems that will help advance the amount of compute that's available. So one of the other things I talked about was data center sovereignty and data sovereignty of, where is my data? There's a whole bunch of work happening using things like GPS and other location-based services so that companies know and countries know that the data and the servers that they say are in a certain country actually are in a given country. And those technologies will evolve and will help relieve some of that regulatory pressure that I talked about. Another thing that's happening is using compute cycles for confidential computing, right? The idea here is that if I encrypt the data, confidential computing makes it very hard for that data to be stolen, right? One of the other problems is someone breaks into the system, your data's there, it's being processed, and they can use it. Confidential computing adds capabilities to these systems that will make things more secure. And then FHE stands for fully homomorphic encryption, which is essentially a future technology that needs a huge amount of performance that allows you to actually work through some advanced algorithms on encrypted data. And so there's a whole bunch of technologies in the compute space that, again, are going to address some of these broken hardware needs that we talked about. Moving on to data movement, at the highest level, what we'd like to do as an industry is move away from electrons that we have with chips today and move to photons, right? The idea is that light moves more quickly, it moves less power, it uses less power when you move it, and it's more reliable, and it's more scalable. We're starting to reach the limits of the data that we can move with electrons. And so there's a number of companies in the industry that are developing technologies that would allow us to essentially take a semiconductor today, convert what it's doing into light, move that to other chips or other parts of a network, and then reconvert it back into electricity for additional processing. So you'll see a lot of work across the next decade of basically optical subsystems doing this. And this also relates to high-performance wireless. This is a super simple example of what I'm talking about. On the left is a picture of an NVIDIA A100 die, which is a high-performance GPU. Across the top and the bottom are something called HBM2 PHYs. It's essentially the physical interconnect that allows the GPU to talk to external memory. On the right-hand side is some technology using graphene, and what that small graphene layer allows you to do is convert those electrical signals into light signals. And the idea here is that we're going to get huge improvements that will allow us to, instead of using physical space on the die for HBM, you actually could just put a graphene layer on the back of the die and convert all the signals into electricity. Faster communication, lower power, more reliability. In the memory and storage space, there's a number of innovations happening as well. There's a technology called CXL that's actually going to make it easier to share memory and move memory within a computer, within a server, and within a rack. There's a number of technologies in memory encryption and memory compression that will allow us to essentially compress and move more data in an easier way, something that hasn't been deployed yet in hardware, or at least not across interfaces. And then there's a number of new memory technologies and archival storage technologies that are looking to address how we store that data when we're not actually computing on it. So this is a simple example of CXL and what you see in a data center. On the top, you see what's called a leaf and spine, typical network in a large data center with a TOR, or a top-of-rack switch. You can see there's a bunch of boxes. They all generate a bunch of power, and they're all moving electrical signals. On the bottom, you see something that's much, much simpler, where CXL essentially removes a whole layer of switches, and those racks talk directly to the spine switch. This will make things more efficient, it'll move data more quickly, and it'll burn a lot less power. So there's innovations that will come into the market over the next few years that will really address this. So moving beyond hardware, that's not just the only way we're going to address this broken hardware to make these larger systems possible. There's going to be a whole bunch of improvement in the AI architectural models. And what I mean is, the original transformer was small, and it could do a certain amount of things, and GPT-3 and GPT-4 and ChatGPT grew larger models so that they could be better at processing large amounts of data. But there's a whole bunch of scientists that are basically saying, well, what we want to do is take those large models, simplify them, make them smaller, maintain the accuracy that they have, and put them on things like phones, or make them more deployable in large data centers. So there's a ton of work happening in the AI architectural space. Another trend, and this is a little technical, is originally I talked about how the models were small, and there was a number of them running together. What the industry is doing is moving from smaller separate models, which take a lot of time to swap in between, and moving to larger models where you can do multiple functions within a single model. This will improve the efficiency and make it, again, a huge improvement in what we can do with a given set of models. Then there's some other technology called sparsity and less precise numerics that, since AI is really based on percentages and a distribution, by using less precise numbers, you're moving less data, you're doing less processing, and that essentially, for the same amount of silicon, gives you higher performance. Sparsity is essentially removing zeros. A lot of a large AI model is zeros. So if you're moving zeros around and trying to process zeros, you're using compute cycles in a non-useful way. So sparsity and precise numerics, or less precise numerics, will remove some of that. There's another increased focus on inference, and the idea here is that instead of just trying to train these large models, let's make them smaller so that we can actually use them to actually process things like voice commands or give you ChatGPT responses. And then the last piece is, I talked about how transformers were really kind of something new that came out in 2018, and now we're 5 years in and we've had these incredible results. But that doesn't mean that transformers are the final architecture of these AI models that we're going to be using to improve our lives and driving this productivity gain. So there are literally thousands of researchers around the world trying to find an architecture that will yield, again, that next big step function in increase in capability that may look completely different than transformers. So again, a number of things that are improving specifically in the AI space on just the models that are being used to deliver these results. So we talked about hardware improvements, I talked about AI model improvements, and now I'd like to talk a little bit about software improvements. And the idea here is, as I mentioned, today AI kind of was a groundswell of capabilities, and as these models grew very, very quickly, we lacked the tools and the compilers to generate these models to make them super efficient. And so we have these large hand-coded libraries that every time a new chip is released, you have to go in, retune the code, put a bunch of engineers on it, and then eventually release it and you could take advantage of it. It's not very fast. The other part is, since these are all hand-tuned, they're not very portable. So if someone comes up with new hardware or a breakthrough set of capabilities, it's incredibly hard to move that model that you've just optimized to a better piece of hardware. But there are a lot of changes happening in the software industry to make it easier to solve and address those different problems, right? So one is open source models. Up until now, a lot of these large models have been very proprietary, but if you've heard of the Llama 2 family of models that Meta released, bless you, they've open sourced those models and made them available to the overall community. Engineers are working on them, they're doing derivatives, they're improving them, and that generates momentum to, again, improve the overall architecture. So the open source software community is absolutely critical to bringing more capability to the marketplace. The other thing that's happening is, if you look kind of on the left versus the right, there's a number of frameworks and compilers that are being optimized, specifically designed to make it easier to give you code portability, so that as an engineer, you can develop code at a higher level, know that it's optimized, and know there's a set of compilers and tools that will allow you to move it to whatever hardware is best for running that model. And that's a change, and that will do things like lower cost and shorten your development cycle, right? Instead of hand-tuning code, if you have a compiler, you have an improvement, you throw it at the compiler, boom, you get a result, and it works better. So a lot of work in the software space between the open source community and just creative engineers creating great products that will make it easier to move these models. Okay, so here's an example of an area where cost and complexity are hugely complicated, and I'll use EDA, or electronic design automation, for chip development as an example. Today, EDA tools take a long time, they take multiple years. You know, I talked about how you have that 4-year cycle to develop silicon. Well, what if we could shorten that to 2 years, right? It would be more cost effective, it would take less time, it would use less compute power. So there's discussion and work going on to talk about how do we move from these tools and start taking advantage of the cloud and AI to automate a lot of this functionality. So what we have are, there's kind of 5 different areas where AI and cloud computing in these large systems could really take advantage of this next generation set of hardware. And in fact, we heard a little bit about this morning, and I kind of want to end with this idea of the virtuous cycle of growth, because it's a very important concept, right? There are new workloads and new things we would like to do with AI. We talked about how ChatGPT is just the beginning, and there's years of things that we want to go do. Well, those new workloads drive a need for increased compute. And when you have a demand for increased compute, that drives innovation, that drives cost reductions, because the cheaper compute gets, the more of it we can use. And then, as I said before, as we get that lower cost hardware, that drives software engineers to do more innovative things, right? And then once those software engineers optimize tools, create new opportunities, new workloads, that enables the next set of workloads. And again, this cycle continues to spin, right? This has worked in the compute industry for years, and I think what will happen with these technologies that we talked about today across hardware, across AI architecture, and across software will really enable this to turn at a much faster rate, and will enable some amazing workloads going forward. So I think as an industry, looking at all these different areas, we really are going to be able to deliver 100x improvement over the next window of time that will really enable these amazing AI workloads. So I thank you for your time, and I look forward to continuing the conversation about what's happening in our industry. Thank you.